Welcome to PhD AI 730 Lecture 04 or fourth lecture, Unlocking Uncertainty. This is Professor T. Mohammed. We will continue from where we left off as of last lecture. As we delve deeper, we'll examine the significance of Markov chain Monte Carlo or MCMC methods in artificial intelligence, particularly sampling from complex probability distributions that are often encountered in machine learning models. MCMC methods enable artificial intelligence systems to approximate posterior distributions of model parameters, as we discussed earlier, when analytical solutions are not feasible, providing a robust framework for inference and prediction. Through practical exercises in Python utilizing libraries such as PyMC3 and TensorFlow probability, we will implement MCMC algorithms to solve real-world artificial intelligence problems. These techniques are instrumental in training sophisticated machine learning models, handling high-dimensional data, and making precise predictions. By integrating Bayesian statistics and MCMC methods into AI workflows, we equip models with the capability to manage uncertainty effectively, thereby enhancing their decision-making processes and overall performance. Now let's look into the core challenges in advanced artificial intelligence that we are dealing with at this very moment. At the heart of advanced AI is a fundamental puzzle, teaching machines not to just make predictions, but to understand how confident or uncertain they should be in those predictions. Imagine a doctor using an AI to help diagnose a rare disease. The system should not just spit out a single answer. It needs to weigh all the possibilities from the patient's symptoms and medical history, and then express its conclusions in terms of probability, such as 70% chance of condition A and 30% chance of condition B. This nuanced reasoning requires the AI to work with complex, multi-layered probability distributions, which are essentially mathematical maps of all possible outcomes and how likely each one is. The core challenge is that these probability maps are incredibly difficult for computers to analyze directly. They are often high-dimensional, meaning they have many interconnected variables like a patient's age, dozens of lab results, and genetic markers, all influencing each other. Performing exact calculations on these intricate maps to find the most probable diagnosis or to understand the range of possible treatments is like trying to solve an immense, constantly shifting puzzle with a pen and paper. It is mathematically intractable, meaning there is no straightforward formula that can provide a precise answer. This is why we need powerful computational techniques like Markov chain Monte Carlo or MCMC. In our medical example, instead of trying to solve the impossible puzzle all at once, MCMC allows the AI to take millions of educated guesses. It randomly explores the vast landscape of possible diagnosis and treatment outcomes, gradually learning which areas are more probable. Over time, these millions of samples build up an accurate picture of the full probability map. This enables the artificial intelligence to give the doctor a complete, statistically sound report that includes not just the best guess, but a clear measure of confidence, ultimately supporting better and safer decisions. The key question here is, how do we perform inference? Example is, what are the most probable model parameters given the data when we can't solve math directly. So modern machine learning models like Bayesian neural networks, BNNs, as we discussed earlier, topic modeling, often involve high-dimensional non-analytical posterior distributions associated. A computational powerhouse for statistical inference, that is what MCMC is. The goal is to draw samples from a complex target distribution such as posterior. It is a hybrid. Monte Carlo uses random sampling to approximate numerical results. Markov chains generate a sequence of samples where each sample depends only on the previous one, eventually converging to the target distribution. Let's look into this with an example. MCMC is a computational powerhouse, as mentioned here, that makes modern statistical inference possible. Acting as a universal sampling engine for the most complex probability problems, at its core, statistical inference is about drawing conclusions from data, estimating unknown parameters, testing hypotheses, and making predictions, but this often requires calculating with probability distributions that are mathematically locked. When exact formulas fail, MCMC provides a master key. It constructs a guided random walk through the vast space of possible solutions. By generating a long sequence of correlated samples that eventually settle into a target distribution, it allows us to approximate integrals, expectations, and other quantities that would otherwise be completely out of reach, turning impossible calculations into feasible computational tasks. This power comes from MCMC's elegant two-part design. The Monte Carlo component means it relies on repeated random sampling to obtain numerical results, much like estimating the area of an irregular shape by throwing darts at it. The Markov chain component provides the intelligence behind the randomness. It generates each new sample based solely on the previous one, using carefully designed transition rules that ensures the chain will eventually forget its starting point and converge to a desired distribution. This combination, strategic randomness with the memoryless progression, enables the algorithm to explore high-dimensional probability landscapes efficiently, navigating through peaks, valleys, and plateaus to map out the true underlying terrain without requiring an analytical roadmap. In practice, this makes MCMC an indispensable tool for Bayesian inference, where the goal is to update prior beliefs with observed data to obtain a posterior distribution instead of solving daunting equations. MCMC allows researchers to simplify by specifying a model, the prior and likelihood, and then let sample generate thousands of or millions of plausible parameters values directly from the posterior. From these samples, we can compute means, credible intervals, and make probabilistic predictions with full uncertainty quantification, whether inferring the dynamics of an epidemic, the parameters of a cosmological model, or the weights of a deep neural network. MCMC transforms abstract probability theory into actionable computational insight, empowering data-driven discovery area across science, industry, and the artificial intelligence. MCMC is a game changer in artificial intelligence. Let's look into this by looking at autonomous driving as our example. As mentioned earlier, in the autonomous driving, we'll look at MCMC's role in this. In the field of autonomous driving, because it allows self driving systems to grapple with the profound uncertainty of the real world. A vehicle's perception stack must interpret a chaotic scene. A pedestrian might step onto the road, a cyclist could swerve, or sensor data from the rain or fog may be particularly obscured. Traditional models might output a single overly confident prediction, like the object is a car 10 meters away. MCMC enables the Bayesian approach, where the system maintains a fully complete understanding of a probability distribution over all possible states. It can continuously sample thousands of plausible interpretations of the scene, varying object positions, classifications, and future trajectories, thereby quantifying its own doubt. This means the car's brain does not just see a single reality, it holds a weighted map of many possible realities of their likelihood. This robust handling of uncertainty directly translates to safer and more defensible decision making. When the systems planning module receives the probabilistic worldview from perception, it can evaluate the risk of millions of potential action sequences through simulation using MCMC to sample from the complex distribution of possible futures. It can calculate not just the optimal path, but the probability of a collision or discomfort for each option. This allows the vehicle to make conservative, risk-averse choices in ambiguous situations, such as slowing down when a parked car's door might open or yielding to a pedestrian who appears hesitant. By integrating MCMC into its core inference loop, an autonomous driving system moves from brittle, deterministic reactions to fluid, probabilistic reasoning, building a foundational layer of caution and adaptability essential for navigating our unpredictable world. The Bayesian inference pipeline, this looks like identifying a problem, define the problem to be solved, formulate a model by creating a mathematical model for the problem, gathering the evidence, collect relevant data to support the model, perform Monte Carlo and related sampling. The use of MCMC to approximate the posterior distribution and update beliefs using Monte Carlo and Markov chains, revise belief based on the new evidence, and then this process can carry on accordingly. The core concept of Markov chain, it's a memoryless property. Next state depends only on the current state. In MCMC, the state is a set of model parameter values. Given enough steps, the chain forgets its starting point at and converges to stationary target. The core concepts continue of Monte Carlo integration. We approximate expectations such as the mean of a parameter using samples, where MCMC provides the correct samples for the Monte Carlo estimate, as we have discussed in the realistic world of humans, where the autonomous car is making a decision while on the road. Metropolis Hastings algorithm, let's understand this in a little bit more depth using a real world example of supply chain. The Metropolis Hastings algorithm finds powerful application in supply chain artificial intelligence by enabling sophisticated probabilistic modeling of highly volatile and interconnected systems. Modern supply chains are massive networks affected by countless unpredictable variables. Sudden shifts in consumer demand, raw material shortages, port congestions, transportation delays, and geopolitical disruptions. These factors create complex high dimensional probability distributions that are impossible to solve with traditional analytical methods. Metropolis Hastings allows supply chain models to perform Bayesian inference on these systems. It can sample from the posterior distribution of critical unknowns such as the true demand for a product given noisy sales data or most probable cause of a bottleneck given conflicting signals from various nodes in a network. This transform this transforms supply chain management from reactive guesswork into science of probabilistic forecasting. A key use case is in demand forecasting and inventory optimization under extreme uncertainty. Traditional models often assume demand follows a known simple distribution which breaks down in the face of the events like a new viral trend or a competitor's supply shock. A Bayesian model can incorporate multiple data streams, historical sales, social media sentiment, weather forecasts, and economic indicators as a complex likelihood. Metropolis Hastings then samples thousands of plausible future demand curves from the resulting posterior. This provides planners not with a single fragile number but with a full probability distribution. They can then optimize inventory levels by evaluating the cost trade offs between stockouts and overstocking areas. Thousands of sample scenarios leading to a strategy that is robust and wide range of possible futures. The Hamiltonian, Monte Carlo or HMC, and NUTS, no U-turn sampler. Let's look into this in the same continuity of supply chain management. HMC and its advanced variant, the No U-Turn Sampler or NUTS, are pivotal advancements in MCMC that solve critical inefficiencies for artificial intelligence applications. But they are not identical. HMC fundamentally reimagines the proposal mechanism for traditional sampler like Metropolis Hastings. Instead of relying on a random walk, which is painfully slow and inefficient in high dimensional spaces, HMC introduces a physics inspired metaphor. It treats parameters, space, as a physical landscape and log probability of the target distribution as negative potential energy. By simulating Hamiltonian dynamics conceptually, giving a frictionless puck, a push HMC generates proposals that follows the counters of the target distribution. This allows the sampler to make distant informed jumps with a high probability of acceptance, dramatically reducing the correlation between samples and converging to the stationary distribution much faster, especially for complex models with many parameters. While HMC is powerful, it requires careful tuning of two critical hyperparameters, the step size and the number of steps in each trajectory. Setting these incorrectly can cause the simulation to be unstable or waste a computation. This is where the no U-turn sampler or NUTS comes in. NUTS is not a different algorithm in spirit. It is an intelligent adaptive extension of HMC. Its primary innovation is eliminating the need to manually set the number of steps. It does this by running the Hamiltonian dynamics simulations both forward and backward in time until the trajectory begins to double back on itself, a U-turn, which signifies it has explored a worthwhile portion of a current energy level by automatically determining the optimal path length for each leap. NUTS makes HMC essentially parameter free for the user while also improving its efficiency and reliability. The Python ecosystem, PyMC3, user-friendly, expressive, Bayesian modeling focused. TensorFlow probability or TFP is another one. Scalable, flexible, integrates seamlessly with TensorFlow for GPU acceleration and deep Bayesian models. You can use that in your upcoming assignments. Topic modeling with LDA, latent direct allocation discovers latent topics in text corpora. The posterior over topics and word distributions is interactable to compute directly. MCMC, such as Gibbs sampling, is the classic powerful method for fitting LDA models. Probabilistic programming. The MCMC enables general purpose probabilistic programming. It defines a generative model of your data, priors plus likelihood, and lets MCMC performs automatic inference on latent variables. It's powerful for anomaly detection, causal inference, and more. I would suggest you to conduct a research in this area to understand in a little bit more depth for your comprehension. Why integrate MCMC and Bayesian stats? Quantifying uncertainty, incorporate prior knowledge, prevent overfitting. Decision making, I will leave this here for you to conduct a little research on Google Scholar or IEEE Explore to understand how people have done the integration of MCMC and Bayesian stats by themselves. Challenges and considerations. The computational cost sampling can be slow for very large models or data. Convergence happens. It must always diagnose, did my chains actually converge? Alternatives are variational inferences, or VI is faster but less exact, often a trade-off. Why? Why should we care? Conduct a little bit in-depth research to understand and establish your understanding. The future is scalable MCMC integration with deep learning frameworks like TFP, as mentioned earlier, for GPU accelerated large-scale inferences. Differential MCMC combining gradient-based optimization with sampling and remains a fundamental pillar for statistically sound, trustworthy artificial intelligence. Happy learning. Hope to see you in the next lecture.